Let's say that your mission is to find a specific value in an array of 1 billion elements. If you don't know binary search, you'll probably implement a linear solution, which in the worst case scenario will have to check every single position to find the specific value you're looking for. But if you had used binary search instead, your algorithm would only have to perform 30 steps instead of 1 billion in order to find the specific element in the worst case scenario. And that happens because binary search has an O log of n time complexity, which means that the number of steps required in order to find the element grow logarithmically as the input size increases, which is much more efficient in that case than linearly. Now, before I start explaining it, it's important to say that binary search only works in arrays that are already sorted, so keep that in mind. On each iteration, we're going to have two main steps. One that we will always execute the same. That will be calculating the average of these two values, the right and the left pointer. The left pointer will always be set at the beginning of the array, and the right pointer will always be set as the length of the array. And then we're going to move our right or left pointer around depending on the result. So, for example, let's pretend we want to find the value 3 in this array. We want to find the index of the value 3. So the first step is to calculate the average of 0 plus 5 in that case, which will result in 2 because we're discarding the decimal part of the value. We're only getting the integer division. And then mid is going to be equal to index 2, which points to the value 5. And then we're going to have 3 checks, right? First, we're going to check if the mid value is equal to the value we want to find. In that case, it's not, because we want to find 3. Then we're going to check if the mid value is less than the value we want to find. In this case, it's not, right? It's greater. So as it is greater, we're going to set our right pointer to be equal mid. And that will essentially mean that we have discarded the right part, the right side of the array. We have discarded all values above 5, and even 5 itself, because this is a semi-open interval, right? We're going to be including the left values, but we're not going to be including the right values since we have already checked the mid value, right? Then we're going to calculate the average again, which is going to result in 1. 1 points to 4. 4 is greater than the value we want to find. Then we set right equals mid again. Now the only value left for us to check is 3. So in the next iteration, we calculate the average again. Mid equals 3. And then we have found the value we wanted, and we return the index of the value, right? So essentially, we're always splitting the array in two again and again by checking if the value is less or greater than the value we want to find, or even equal, right? In that case, we don't even split, we just return the index. The actual implementation looks like this. We're gonna set the left pointer to the index 0, the right pointer to the array length, and we're gonna have this while loop with this exit condition that says that we're gonna execute, we're gonna be splitting the array and looking for the value while left is less than right, because if ever left is equals right, it means that the value is not in the array. The value we're looking for doesn't exist. You might see other implementations with a closed interval, but I prefer this semi-open interval implementation because if we have a closed interval, we have to set more edge cases. For example, in the right pointer, we will have to set the value to be the array length minus 1, and in this while loop, we will have to set the exit condition to be while left is less or equals right. And when that happens, when we set many edge cases, it might get a little bit more complicated to implement this algorithm in other contexts. So we want to keep it simple. As we want our algorithm to handle any valid input case, we also want to eliminate the risk of an integer overflow. And if you don't know what an integer overflow is, we have this example here. Int in Java is a 32-bit signed integer. So we have these possible values here. And basically means that if we perform an operation that the result is greater than this value or even less than this value, we're going to get an integer overflow, which means that the operation will not be precise. We cannot store in an integer a value that's bigger than this one or less than this one, okay? And in our code, we always perform this operation to get the mid of the array, right? And we definitely could have a massive input. And when we would ever perform this operation here, this sum, we would get an integer overflow. The solution for this is finding a mathematical equivalent formula. So in Java, you would use this line instead of this line, right? But as we're in Python, Python is much more flexible. It handles it without us having to deal with it, right? And that's it. Binary search has a O log of n time complexity because it scales logarithmically, and it has a O of 1 space complexity because we always keep a constant number of variables in memory, right?